My spring break was mostly just doing, trying to catch up with chores in around the house and grading. Yeah, that was pretty much in my entire break was that. But it was okay. I caught up with a good amount of grading. There's still a lot to go. But thank you for asking. I hope you guys got a relaxing break, but also at the same time, you'll still have time to kind of keep the engine warm, so to speak, so that you're not gonna start with a cold engine today. All right, so I'm just checking on Discord. We got about 10-ish people on Discord and no one on YouTube. So, according to my stats, nobody is on YouTube right now, which is kind of interesting. Oh, okay, it's showing 7 concurrent viewers. Okay, so there we go. All right. All right, so I am reading the text in the text channel. Um, suppose later on we can present an example, but right now I think it's kind of important. Well, I can actually mix it into whatever the topic that we're going to talk about today because that's going to use a lot of labels. So we'll talk about what labels really are, okay? Because they're a convenience feature, so that you don't have to count bytes when you need to specify, okay, where am I going to continue execution after this point? Well, I mean, you can if you want to do all the byte counting, but it's going to drive you crazy after a while. So, generally speaking, we want the assembler to keep track of all that. And when we want the assembler to do that, it means we need to have a way to refer to those locations symbolically, and that's basically why we have labels, or one main reason why we have labels. There we go. Alrighty, so I think we are good to go, and we are going to get started now. Alrighty. Alright, so somebody just posted something in the general text channel, which I am not going to check right now because we have to stay on the channel of today's date, because otherwise I have to switch between the channels and it's not going to be efficient to do that. All right, so today's focus is going to be compiling. I know what that sounds like. It sounds really kind of difficult but this is not a compiler class. So I'm not asking you guys to write a compiler. I'm asking you to manually translate the logic in C, C++ programs into TTP ASM. All right. So what we'll do is we're going to start with this module, which is compiling in double quotes C control structures. Compiling is in double quotes because I'm not asking you to write an actual compiler. We are basically doing some kind of manual translation between C control structures and TTP ASM. And before anyone complains and go, but C was not a prerequisite of this class, C is a subset of C++, and C++ is CISP360, which is a prerequisite of this class. So there we go. All right, so we'll go into this particular module. And there we go. Alright, so this is a rather long module. If you just look at the thumbnail on the right hand side, you can see it's really kind of long. Maybe you cannot see it because my face is blocking it, but it's kind of long. The reason why it's kind of long is because of the example at the end. Section 7 is a really long example, so it basically is a bunch of code that is there are many revisions. Okay, one revision for one little thing, so I'm trying to show you guys how to do the translation in steps. So let's go ahead and get started with the three control structures that we are most concerned about. Section 3.1 talks about conditional statements. This is a general conditional statement in C, C++, Java, JavaScript. There's a whole bunch of languages out there that share the same syntax. So C here, okay, this C here. Let me just highlight it. It's a condition. So when you see C, as a letter, it doesn't really mean that it is register C or variable C or anything like that. It's basically a placeholder. It's a placeholder that is representing the condition of the conditional statement. And then block one here is once again a placeholder. It means we have some block of code to execute when the condition, if and only if the condition is true. And then we have another block of code to execute if and only if the condition is false. So that's the general structure of a conditional statement. And it doesn't really matter what programming language you're using. Almost every single programming language offers a conditional statement like this. Now, the next part is specific to C, C++, because you can actually write a program using labels and gotos, even though your professor probably did not want you to use gotos at all. But the bottom line is this chunk of code, which does make use of gotos and labels, is equivalent in terms of what it does with the original code, which is what I would call a structured statement. So let's take a quick look here. With the translated code, if C is false, we continue execution at label L1. Label L1 is saying, okay, we have the same block 2 here, which is what we want to execute if and only if the condition C is false. And you can see how that behavior is replicated by the kind of uglier version of the same code. So what if C is true? Well, if C is true, then not C is going to be false. If not C is false, then whatever statement after the condition, in the conditional statement, is not going to execute. Instead, it's going to fall through to block 1. And block 1 does correspond to block 1 over here, which is what we want to do if and only if the condition C is true. So are we looking at this and understanding how this code is equivalent in terms of the first part of code here, this chunk of code which is structured, and this chunk of code here which is not structured. So if you have any questions about the equivalency between these two blocks of code, now would be a good time to ask. All right, I am not seeing anything in the text channel. So are we all good? Are we ready to move on to the next statement, to the next statement type? All right, all good, and all right, so Omer is typing, so I'm gonna wait a little bit here. All right, all good. All right, excellent. So the next variant is basically just the same as what we see here as a conditional statement. The only thing is, what if block 2 is empty? Because a lot of times, there's only something to do if and only if the condition is true. And if the condition is not true, well, we simply don't have anything to do. In other words, what if block 2 is an empty statement? Well, as it turns out, you can skip, the else portion if there's nothing to specify. So this is, basically a specialized version of a conditional statement where there's no else statement. And the equivalent form of this conditional statement here is captured here, which is kind of makes sense, right? Because all it says is if C is false, then skip over block 1. Don't do anything, just continue execution at label L1. And it has to do with when block 2 is empty, when this block 2 here is empty, then you really you can just do it like this. Okay, you can actually use this form and just leave block 2 as an empty block. But in that case, you're having a go-to, which is going to label L2 to continue execution at the statement right next to it. In other words, this go-to and then this L2 here is serving zero purpose when block 2 itself is empty. So that's why we can have a slightly more simplified version when we want to perform the translation when there are no else statements to perform. All right, moving on to section 3.2, which is the pre-checking loop. This is what I would call a pre-checking loop. I know most other professors will simply call this a while loop. A while loop has a condition. Once again, C is a placeholder, so is block 1. And the idea with a while loop is we check the condition first. If the condition is true, then we go ahead and perform whatever block 1 is, and then we go back and check condition C again. If and only if condition C is false, we get out of the while statement, and then we continue execution with whatever is after the while statement. So this block of code is nice and structured, and when you want to ask what is structured and what is not structured, typically when you see the use of braces, it is structured. When you do not see the braces anymore, it is no longer structured. So that's why this block of code here is not structured, because it is not using braces to express what statement is nested within what other statement. So when you look at this statement here, once again we check C, but you have to look carefully because there is an exclamation point before the C. So if and only if C is false, we go to L2, and L2 is our escape route. And once we get to L2, we continue execution with whatever is after this block of code. So the only chance that you can the only reason why you would perform block 1 is C itself is true, because if C is true, not C is false. If not C is false, then we are not going to execute the go-to statement, which means we fall through to block 1. Then we perform block 1. After block 1, we have an unconditional branch to go back to L1, because that's the whole purpose of a loop, is to go back to reevaluate condition C, or in this case, the negation of condition C, and see if it is time for us to exit the loop. So are there any questions about section 3.2 regarding why the structured code that looks like this is equivalent to the unstructured code that looks like this? So if you have any questions about the equivalency, now would be a good time to ask. Alright, so it looks like there are no questions. Alright, not a problem. Then we shall proceed to post-checking loop. So this is what I would call a post-checking loop. Most people would just call this a do loop or do while loop. I use these terms of pre-checking and post-checking because it does not refer to the polarity of the condition, because a do while loop is also, I wouldn't say equivalent, but it is closely related to what we call a repeat until loop. C and C++ does not use repeat until, but many other languages do. And in the case of repeat until, the condition is the reverse condition. In other words, you specify the exit condition when you have a repeat until condition. With a do while loop, you specify when or under what condition do we stay in the loop. So this one is actually easier when it comes down to the unstructured code, because with a do while loop, you perform block 1 first. Okay, you do not have any condition to check first. You simply perform whatever action is associated with the loop. Then you check the condition C. If the condition C is true, then you go back to the beginning and you perform block 1 again. If condition C is false, then you stop the loop and you continue execution with whatever is after the do while loop. So in this case, the unstructured code is very simple because in this case we just need to label L1 to designate the place where we have to go back to just in case the condition is true, and then we specify block 1. Remember, block 1 is really just a placeholder. It can be one single statement. It can also be a whole chunk of your statements. We don't really care because we just want to look at the control structure itself and be able to translate the structure itself into something that is not structured. And after block 1 we have a conditional statement, and this time C is not negated. This is just C by itself, which means if and only if C is true, we go back to label L1 so that we actually end up performing block 1 again. If and only if C is false, then we do not perform the go-to statement, which means we just simply fall through to whatever is after the conditional statement here. All right, so we are done. We are done with all the basic control structures in C and C++. And someone may mention, what about a for loop? Well, a for loop is really a fancy version of a pre-checking loop, where the initialization is built in to the things that you specify within the parentheses, and also the post operation is also specified, as the last item in the parentheses, and those items are semicolon separated. So a post-checking loop, a pre-checking loop, is basically the core of what a for loop is. It's just that in the case of a for loop, it's more convenient to specify the initialization as well as the post operation. So that's why we do not specify a for loop in as one of the control structures. The only other control structure that is really useful that I do not express here is a switch statement. A switch statement is not expressed here because a switch statement can be translated into a chain of conditional statements. So you basically just have if, and then else if, else if, else if, else if, and then else, sort of, not exactly, and that's because in the switch statement, if you forget about the break, at the end of a case, it would simply fall through to the next case, and that effect is not going to be the same when you replace a switch statement with a sequence of if, else if, else if, else if. So that's the kind of the caveat of using if, else if to implement a switch statement. Switch statements are handy in some cases, but they are also extremely, I personally do not like switch statements, at least not the way they implement it or the way they specify the construct in C and C++, because you have to specify a break statement in order to say, okay, this is the end of this case. Do not continue and fall through to the next case. If you're not sure what I'm talking about, that probably means your CISP310 professor did not teach you everything that that person is supposed to teach you, because a switch statement is part of the core control structures of C and C++. It's useful. It's just that it is also tricky to use in many cases. All right, so do we have any questions about section 3 in general? I'm just going to pause here and make sure that we are ready to move on, because this is, in a certain way, this is pretty easy stuff, but it is also predicating on the fact that we all understand what is a conditional statement in C++, and specifically what is the proper syntax of a conditional statement. So without that knowledge, these statements here can be very confusing. So I just want to make sure that we are all good here before proceeding to talk about something that is potentially even more confusing. All right, so case statement is a switch statement. No, a case is within a switch. Let me see if I can do this. I did not prepare to capture my own notes today, because this actually does a lot of what I need to do already. So I'm just going to use Notepad here. So when you use a switch statement, it typically looks like this. Okay, you basically say switch, and then this is some kind of expression that will give you a specific value. Most of the time, the value is going to be some kind of an integer, and then you specify, okay, if expression equals to constant 1. Okay, so this is where you use a case, right? Because you say case. I cannot even remember whether this is the proper syntax or not. So if expression gives you a value of 2, then it will switch to this particular branch, and then you perform some kind of statement. Yeah, so you have a bunch of stuff here, but if you forget about this break statement at the very last part here, and then you have a case 3 down here, without this break, whatever you execute here is continuing on to break into case 3 if the break statement is not here. And that's why it is really important in a switch statement to remember to use a break, which is what you want to do in most cases. There are very few cases where you do not want the break and you intend to fall through to the next case, but those are very, very few and rare cases. Most of the time you do want a break so that you stop the execution of these dotted dots and not to continue to whatever is after case 3. All right, so there's that. Any other questions about section 3? Because section 3 only talks about the structure, the control structures, which are basically types of statements. In C++, it doesn't quite talk about, but what about the condition? How do we deal with, those conditions? What if the condition involves an AND or logical OR? What if it has a logical NOT, and so on? So we are going to talk about that in a later section. So right now we just want to make sure that all the control structure stuff is okay. Alright, so I'm looking at the text channel. So far I have not, there are no questions. Alright, so if there are no questions in the text channel, we are going to move on. Alright, so I'll probably present an example, after all of this is done. And then we'll go from there. Alright, so conditional goto and Boolean operators. That's basically asking the question, what if this C here, okay, let me highlight which C we are talking about. What if this particular C, which is a placeholder, is a complex Boolean expression instead of just something that's simple? So what section 4 is trying to do is to say, okay, if C is a negation of something, you can see how there's a negation here, and then there's a C, which is once again a placeholder. You can get rid of the negation by translating this statement here into this statement over here. So all you're doing is you're getting rid of the negation. So now you're reducing the complexity of the condition because you're getting rid of the last operation, which is a logical negation. And instead, you are complicating the use of gotos and also the use of labels. But it does work the same way because in this case, you are going to continue execution at label L1 if and only if C is false. So in this case, it has the same effect because if and only if C is true, you would end up at label L2, which is the continuation point of whatever is after the original control structure. So the only chance you have to go to label L1, which is done by this particular goto statement, is you do not go to label L2, and you do not go to label L2. The only way you do not go to label L2 is C is false. So it ends up having the same effect as this statement here. It is a little bit longer, it is a little bit more clumsy, but the point is we are getting rid of the negation operator that was in the original expression. So that's one, okay, that's for negation. And section 4.2 deals with a OR. So once again, C is a placeholder. C by itself can be a really long and complex Boolean expression. And the same thing applies to D. D can also be a very long and complex expression. But at this point, we don't care because the only objective that we have now is to get rid of the OR, logical OR operator. so that we can reduce the complexity of the condition that we're dealing with. So in this case, the only chance, the reason why you would go to label L1 is C or D is true. Now we know that with a logical OR, now this is a logical OR, not an exclusive OR. So this is a logical OR, which means if at least one of C or D is true, then the entire disjunction is true. In C, C++, and most modern programming languages, the order of evaluating C and D is fixed. It has to be going from left to right. And that has to do with the short-circuited method of evaluating Boolean operators. What that means is if C is true, don't bother to evaluate D, because if C is true already, then the disjunction is guaranteed to be true already. So why do you want to waste time to compute D when you already know that the overall disjunction is already true? So that portion should also be taught in CISP360. There are a few names to refer to the same mechanism. The one that I just used, which is short-circuited evaluation, is quote-unquote the formal name. The second name is just lazy evaluation. Okay, you're trying to do as little as possible to come to the conclusion of what the disjunction is going to be. So when you look at the replacement code, it will do exactly the same thing. Okay, if and only if C is true, we go to label L1. In other words, if C is true already, we don't even bother to evaluate D, and we just go straight to label L1, which was originally where we wanted to go when the disjunction is true. Now, what if C is not true? If C is not true, then we're not going to go to label L1, and it will fall through to the second conditional statement. Then it would evaluate the condition D, and if D is true, then we still end up at label L1. On the other hand, if C and D are both false, then we will end up continuing to execute whatever is after these two conditional statements, which is equivalent to what this statement would have done if C and D are both false. So do we have any questions about section 4.2, which is translating a Boolean expression that has the last operation is a logical OR into something that's simpler? In other words, we take the left-hand side and say, okay, now we have to deal with this on its own, and then we take the right-hand side and then we say, now we have to deal with it on its own, but the disjunction is gone. So this way we can basically step by step reduce a complex Boolean expression into something that we can handle. Alright, so we got a few people typing. I'm gonna wait for those questions. And once again, it's important to understand that C and D here are not names of registers. Alright, so what was the other name you used that lazy evaluation? Oh, it's short-circuited evaluation. Short-circuited Boolean expression evaluation. Short-circuited Boolean expression evaluation. And I spelled it wrong. Good thing I have not pressed the enter key yet. There we go. And for those of you who are visual, I'm going to show you something that is visual. There you go. That would make it really easy to remember. For those of you who are old enough to remember this movie. Alright, so Chris is asking, that is an old reference. It is very old. Johnny 5 is, that's the name of the movie. Short Circuit is the name of that movie. Alright, so Chris is asking, is L limited to L1 and L2? Nope, I'm just using L1 and L2 here because I don't want to imagine additional names. So no, L1, L2 you can name the labels anything you want as long as it can also be used as a C identifier. That's the general rule of what you can use as a name of a label. So label and L1 and L2 are just here because that's the simplest thing I can do to basically name the labels. There's no intrinsic meaning to 1, 2, or L. They just mean being lazy, not wanting to come up with inventive names for the labels. That's all. All right. So in a large program, well, that's what the compiler has to handle. The compiler internally has to handle like a lot of labels. Um, and the worst thing about labels is it is visible within the same function. So you cannot reuse the same name within a function because labels are quote unquote um, they're visible within an entire function. I think different functions can share labels. I'm not 100% sure. I can test it really easily, but I'm not sure about that. Yep, in a large program. So the point of a large program is you don't want to write the entire program with one file. You would basically separate and write one function in one file. That's the general approach when people write large programs in assembly language is they use one file for one function. And then they would need to use a linker to basically resolve all the external references within a file. But we are not going to get that fancy in this class because our entire RAM, which is what you can use to store your program, only has 256 bytes, and that's including the stack. So we are not going to write any program that's going to be really long to begin with. So, but Chris is correct. You basically have to deal with a lot of labels if you are not writing a program in a high-level programming language, and instead you're writing a program in assembly language. Very good. Any other questions before we move on to and? No questions. Okay, I'm not seeing or hearing any questions. So we are moving on to conjunction. So in other words, what if the original expression is a conjunction? So we would do something slightly different this time because what we will do is we are going to say if not C, go to label L2, which is our continuation point. That kind of makes sense, right? Because this is also short-circuited evaluation. Because if you are dealing with a conjunction and one side is known to be false already, then the whole conjunction is going to be false, which means there's no need to evaluate the other condition. This is also why when we get to or, which is bar bar, and, which is ampersand ampersand, those strictly follow the left to right order when we evaluate the expressions. Now, when you're dealing with plus, okay, just arithmetic addition, there's no guarantee of the ordering of whether the compiler will crank out the code for the left-hand side first or the right-hand side first, because addition is commutative, which means you can flip the order. It doesn't really matter. But someone is going to say, but tech, isn't disjunction and conjunction both? They're also commutative, where A or B is the same as B or A and B is the same as B and A. That is correct. From the perspective of Boolean algebra, that is correct. However, when it comes to the behavior of the program, they are not identical. That's because a lot of times, especially when we are trying to make sure that your index is within range, when we're trying to go through items within an array, we first check whether the index is still within range, and then we check whatever else that we need to check. Like, okay, now that we know I is within the range of valid indexes, now we can look at the item at index I and blah blah do something with it. Okay, so we actually use short-circuit evaluation or lazy evaluation a lot of times, and that's why it is very important that we only evaluate from left to right and not say, oh, but we can flip the order because in terms of Boolean algebra they should be the same thing. So does everybody understand that point? Because it is a very important point. It is not exactly a point that I should be making in CISP310, but I am getting the feeling that that point probably may not be made in CISP360, which is the appropriate context where that point should have been made. So are there any questions about the why we have to strictly follow the order of left to right when it comes down to conjunction and disjunction? All right, maybe not. So if there are no questions, we're going to finish up, conjunction. So with conjunction, if not C is true, which means C is false, we go to the continuation point, because if C is false, might as well just kind of give up hope to go to label L1. On the other hand, if C is true, then not C is going to be false, which means we fall through to the second conditional statement. The second conditional statement is going to check whether D itself is true or not. If D is also true, then and only then we will end up at label L1. All right, so we got a text here, but aren't you going to remove the not sign and then write it in assembly language? Well, no, I'm going to invoke this logic recursively, because this is falling into the pattern of, guess what? Section 4.1. So we will get to section 4.1 and perform that translation here. So so this whole thing, okay, what we have been talking about here is only these are rules, okay, these are patterns, okay, that can be applied in a recursive way. And most people only use negation, conjunction, or disjunction when they specify a Boolean expression. So that's why we have only these three in sections 4.1, 4.2, and also 4.3. So I hope that addressed Bilal's question of whether I'm going to remove the not sign, because I don't have to. We already have a pattern. We already have a rule to deal with a logical negation. And that's section 4.1. So I just say, we'll just do this recursively. Apply these logic recursively. All right. Any other questions? All right. What does recursively mean? That means you basically look at this and then you reapply these rules from the beginning. You look at section 4 from the beginning and say, am I seeing something that fits this particular pattern? If so, then we translate that into this pattern here. So this is all about matching a pattern and then re-express that pattern using a different pattern. Now obviously the labels will all have to be changed, because you cannot reuse label L1 and L2 all over the place. But the bottom line is, okay, these labels, assuming they are unique in the context where they are defined, that's how we want to translate the code. So recursive is the term recursion, or the adjective recursive, and also the adverb recursively. Those are very important concepts that really should have been introduced in CISP300, let alone CISP360. At least when I was teaching CISP300, I talked about recursion, because it's a very important concept for in computer science. I'm not sure what I can do at this point, okay, now that we are already in CISP310. I can only try to explain recursion as much as I can in this class, but those concepts are very, very core to programming and should have been introduced in CISP300. I can already see some people saying, but Tech, you're just pushing responsibility to other professors. No, I'm not, because I actually wrote the curriculum for CISP300. So people have not been teaching that class as it is specified in the curriculum. That might be the issue. All right, so if we apply what we have learned so far, okay, section 3 has to do with statements. Section 4 has to do with Boolean expressions. Eventually, will boil down to something that cannot be boiled down any further. Okay, so what those things would end up as, okay, would be comparisons, because every single condition has to boil down to a comparison. Um, and someone may say, but what about you have a Boolean variable and you're just checking whether the Boolean variable is true or false? That does not involve comparison, right? Well, it does, okay, because you are basically implicitly comparing that to true or 1 or anything that is non-zero. You're testing whether it's non-zero or not. So testing whether something is non-zero is a comparison. It is comparing to 0. So everything boils down to, all conditions eventually will boil down to comparison. So what about comparisons? Well, in comparisons, we are first going to kind of go back to something that we have talked about a little bit before. X is less than y is just x is less than y. X is greater than y can be reversed. You can instead check whether y is less than x. X is less than or equal to y can be boiled down to x is less than y or x equals to y. X is greater than or equal to y, you just flip the order. You can just check for whether y is less than x or x and y are the same. X equals to y is fine, and then x does not equal to y is the negation of x equals to y. So why do we care whether x does not equal to y can be expressed with a Boolean operator combined with equality check? And why do we care whether we have a whole bunch of less than or equal to boils down to equality in one comparison, which is checking less than? So why is that important? Oh, thank you. Thank you, Omer. That might be helpful. Okay, so for people who have not experienced recursion before, any resource would be good. All right. So, getting back to our focus here, which is why do we want to translate everything, all the different kinds of comparison, down to some kind of logical operation combined with the confirmation of less than or the confirmation of equal to? Why is that important? I'm going to let you guys think about it a little bit, in terms of the context of this class. You kind of have to think about the flags, okay? The flags, and also when we talked about binary comparison, what is the basis of binary comparison, and what flags would be the result of binary comparison, and what does it mean when those flags are ones? So those are the questions that you might want to ask. Is that okay? I mean, are you guys kind of making the connection between what we are looking at here with binary comparison, the flags in binary comparison, and also the Z flag, which was not mentioned in binary comparison, but it was mentioned earlier, like maybe a few weeks ago. So all of those things are connected. So I'll give you a brief answer. Oh, okay, Omer is typing, so I'm gonna see if Omer is answering this question or not. Alright, so we would be checking the values of certain flags to evaluate if something is less than or greater than. Yeah, so that's kind of the bottom line. So what I'm going to do now is I will give you a few kind of random examples of, how do we translate that into assembly code. So now, now is a good chance, I can explain, what a label is, and also actually test run the code. Alright, so I am switching to this screen here, and I'm gonna get rid of this because that's just for explaining a construct that I decided to leave out because it's just not a very useful construct from the perspective of most programs. Alright, so we're gonna use a program here. We'll say int 8 underscore t A, B, and C. Okay, so these are basically registers. you really cannot directly address or specify registers in C++ code. But we'll pretend that we can, okay? Because we haven't really talked about the local variables or global variables or how to access those variables. So we don't really have a mechanism to talk about. Oh, so we can now compare the value of this variable to the value of that variable. We don't have any mechanism to do that. So right now we're just going to be using registers. So assume these are in registers. All right. So let's just say that we want to do something like this. Okay, so let's say we want to say if a is less than 5 and a is greater than c, and if that is true, we want to do something like this: b equals to a plus c. Okay, now don't ask me why we want to do that, because I'm just randomly spewing out some code just as an example. That's all I'm trying to do here. In that case, b is c minus a. Okay, so that's the code that I need to translate. All right, so the first thing is, how do I do this? How do I translate this C code into TTP-ASM? What would be the first step that I need to do here? What is the first pattern that I am going to recognize and go like, it meets it matches this pattern here. I'm going to apply this process and translate this code into equivalent but uglier and not structured code like that. Yes, we are going to look at the conditional statement. So we are going to apply section 3 first, and then we're going to apply section 4. All right. Look at the guide behind your notepad. Yep. Well, I don't have to look because I wrote that stuff, right? Well, that's actually not true, because sometimes I actually forget about what I have written in the past. All right, so we're going to match this and go like, okay, so we can translate this into if blah, 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 go to, I'm just going to say, else label, okay? And then we have b gets a plus c here. And then we have j go to, and if label. And then we have else label defined here. And then we have b gets c minus a. And then we're going to have end if label defined here. And of course, we're going to have to backfill this. Okay, this is supposed to be the negation of the original condition. So the original condition is this one here. So I am just going to copy and paste it into this pair of parentheses, and I am done with one step. Okay. Are there any questions about what I just did, how I did it, or where in the content that we have already talked about today that I mentioned about this? I mean, obviously, I did not use label L1 and L2. I chose to use some slightly more meaningful names for the labels. Won't it get confused with the labels? You have more than one if statement. Oh, yeah. Yeah, so you have to come up with new label names if you have nested statements. Yes. But I'm going to tell you there are ways to generate those names in a much more systematic way, so you do not end up with the same label name again and again. So we'll leave that discussion till later, and when we need to do that. But right now, since we only have one single conditional statement to consider, this should be okay. All right. Also, I was wondering when you were going to explain the value labels have I asked before lecture started. All right. So right now, this is C code, right? This is C code. It is not in assembly code, so we are not quite at that point yet. But it is important to understand that label definition is the same whether it is in C code or whether it is in assembly code. All this label else label is trying to do is to say this is the location where we start to do this particular statement here. That's all it's trying to represent. It's just representing a place. It's representing a place in your program so that you can refer to that place by its symbolic name. That's it. Would that suffice, Bilal? Would that explain what a label is? Why would it be 0? It has to correspond to a location in whatever memory your program is put into. Whatever this code is not going to be at location 0. So why would the label be at location 0? So you don't count it when you are counting lines. So you're only counting instructions. Well, eventually everything boils down to instructions. And each instruction has its address, which is basically some, in a large program, it's going to be like 64-bit wide. I mean, it's not something that you want to deal with manually. That's why we want to use labels. I mean, if you have a program that's like, okay, let's say you have a tiny little program that's 3 megabytes. That's 3 million locations, right? So so each location is going to be it's going to be 7 digits in base 10. You can kind of imagine how long that's going to be in binary, right? Because 1000 is about 1024, which is 10 bits. So a million is already, we're talking about 20 bits already. So, a 3 megabyte program is going to have to specify, locations in base 2. It's going to take 22 bits, 22 zeros and ones. I certainly do not want to deal with that. I don't know. It's up to the assembler to get to it, right? So just wait until I'm done with this, and then when we put this into the assembler, then it'll be clear. All right. So Ian is also typing something, and I'm gonna wait a little bit. All right, will you be explaining how little endian works? Okay, so it's a useful concept, but it is unnecessary given the context that we are in, because TTP-ASM, each location is only 1 byte, but all the variables that we are going to use are also only 1 byte long or 1 byte wide. So endianness, does not matter. We can certainly talk about big endian versus little endian when we have time. Okay, so you can remind me if we have time left at the end of today's lecture. We can go back and talk about endianness, but it is not essential to what we need to deal with here. Alrighty, so now we look at this modified program. Yeah, so you can kind of put it on a list of things that you want to go over when we have time. So when we look at this code here and we say, okay, can we look at this and fit it into one of the patterns of section 3? The answer is no, it does not fit into anything in section 3 because we don't see braces anymore. This is not structured code anymore. So now we look at this and go like, okay, so if we're not going to apply anything in section 3, we're going to be doing something in section 4 instead. So in section 4, we look at this complex Boolean expression and go like, okay, so how do we boil this down to something that's simpler? The first thing people see would be the negation here, right? Yeah, so it seems like, we can apply section 4.1 and try to get rid of the negation. Well, fortunately, in Boolean algebra, we also have De Morgan's law. So we're going to use De Morgan's law, which is a trick in Boolean algebra, so that we don't have to perform section 4.1. So for those of you who cannot remember what is De Morgan's law, Morgan's law. So in this context, De Morgan's law basically say if you have a negation of some kind of a conjunction, and we'll label these two as x and y as placeholders. So this expression eventually, would actually be the same as not x. Okay, let me use parentheses to make sure that we are clear in terms of what operator applies when. All right, so that's De Morgan's law. De Morgan's law basically say if you have an expression that looks like this, it's actually going to be equivalent to this expression over here. In CISP 440, which I'm also teaching, I tell people, okay, if you do not believe this, okay, that's okay. Use a truth table, and then you can easily convince yourself that these two expressions are indeed the same thing. So we're going to apply that. Okay, so once we apply that, then someone is going to say, but this is worse, Tacky. You're just making a problem even worse, because now we have the negation of a is less than 5, and then we have the negation of a is greater than c, and that doesn't seem to be any better. Okay, go to else, label, and then the rest we can just copy and paste, because I am just focusing on the conditional, the condition, which is a Boolean expression here. So copy and paste here. All right, so we look at this and go like, wow, that doesn't seem any better. Well, I think it is better. I think it's better because now we don't have negation. And instead, we just have the two sides of disjunction to deal with, right? This is one side of the disjunction. This is the other side of the disjunction. So now we can apply section 4.2. Okay, see, even I can remember, the section number referring to, what operator, can be processed, in what way. Okay, so that's going to be section 4.2. So let's go ahead and say, okay, what does section 4.2 say? Section 4.2 basically say, since this is a disjunction, we just basically check each one individually. Okay, so if not a is less than 5, go to else, label, and then we check the other one, which is if not a is greater than c, go to else, label, and then the rest of the program, guess what, is exactly the same as before, because all we are trying to do here is to get rid of the disjunction in the condition. Alright, so I'm going to pause here just to make sure that everybody is catching up with the discussion here, and if there are any questions, go ahead and ask. Not seeing any questions. Alright, well, if there are no questions, we're going to move on. So if you need to take your own notes, you can kind of say, okay, I'm going to do it for you. After applying section 4.2, and this is after applying the Morgan's law. All right. So now we look at this code here and go like, okay, so we are still not seeing everything that can be done in assembly code. So what is next? Well, you feed this back into the pattern matching engine thing, that we were talking about in section 4, and then we notice, aha, we can see a negation here, we can see a negation here. But this time we are negating a comparison already. So that means, in order to get rid of the negation, instead of applying section 4.1, which is what we need to do if there's absolutely no other way to do it, right? But since in this case we can do some algebra, this is not Boolean algebra, this is just straight up algebra. So straight up algebra says, we can just kind of get rid of this and convert the less than into greater than or equal to, and in this case, we get rid of the negation and turn the less than into greater than into less than or equal to. So we just use algebra to get rid of the negation, because you don't really want to apply section 4.1 unless it is absolutely necessary, because it just makes the code a lot uglier and also more difficult to. The program is going to be longer, which means it's going to be less efficient as well. So are we good here? And here I'm just going to say after applying algebra. There we go. So if you have any questions, you go ahead and ask away. So we're good. All right. Okay. Thank you for confirming. It's good to have the confirmation, because otherwise I can't see your faces, right? Because that's one reason to go back to face-to-face mode in the fall. I'm teaching on the ground, face-to-face, 100%, in the fall semester, because I need to be able to see your faces in order to assess whether we are ready to move on or not. All right, thank you. So we shall move on then. All right, so now we look at this and go like, but Tack, hold on a second here. We can confirm equal to, we can confirm less than, but we cannot confirm greater than or equal to. We cannot confirm less than or equal to. Wait, hold on a second here. Did I just say less than or equal to? Doesn't that mean it is separated into less than and then equal to? Ah, okay, so maybe we do have a way to deal with that. But before we go there, we're going to have to flip the ordering here. Okay, so this is once again just a regular algebra, but we are converting everything into less than and equal to. Okay, that's important. All right, so we copy and paste again, and I can imagine at the end of today's class somebody's going to say, can we have your notes here so that I'm not going to have to retype the whole thing on my side? Maybe. All right, so we're going to convert this into two separate comparisons, right? So we have, so we can first check for less than, okay, and then we can check for equal to. So 5 equal to A. Now, this is really important. Once again, this is something that should have been covered in CISP 360 as opposed to this class. This has to be a double equal, not a single equal, because we are not performing an assignment operation. We are trying to compare two values and see if they are the same or not. Okay, so just a little bit of extra stuff that I'm going to remind you guys. I'm pretty sure most of you know this already. This one is not so much. Okay, if you do have a typo and it becomes 5 equals A, the compiler can catch this just like that, right? Because you cannot change a constant. A constant is not a variable. It doesn't have a what we call an L value to update. So this one is easy to the compiler will catch it. This one, not so much. Okay, if depending on whether you enable all the warnings from your compiler, this is actually syntactically legit. Okay, because all you're trying to say is, oh, we'll just copy whatever C has to variable A, and then we'll see if A is non-zero or not. Okay, so the compiler may not give you a warning depending on how you set it up. I'm just telling you guys all this stuff here because obviously I have been bitten by this sort of stuff a lot of times. So I learned my lessons. The suspense. All right, so this has to do with reducing to less than and shift and equal to. All right, so you look at this code and go like, okay, so what can we do now? Well, what we can do now is we can now start to translate into actual assembly code. All right, so if we are to translate into assembly code, how are we going to do it? So I'm commenting out the C code now because I'm actually going into TTP-ASM. So TTP-ASM code follows. There we go. All right, so now in comparison, okay, you cannot do this. Okay, there's no such thing as CMP5A, even though that would be handy, but we cannot do that. Why not? I have just finished grading exam 2, and this question that I just asked, which is why can't we compare a constant of 5 to a register A, is closely related to question number 2 of exam 2. But it has to do with the architecture. It has to do with the architecture. There is no pathway to specify an immediate value and connect it directly to the ALU. The ALU is the only thing that can do the comparison because the subtraction operator or the subtraction component is in the ALU, and there's no way you can actually connect from RAM, which is the only place where you can specify a constant, just like what you can do with LDI. So there's no way to specify this instruction. It is not because of the syntax, it is because the architecture itself does not have a pathway to do this. Okay, so this is really important because I'm trying to relate what we are seeing here, because trust me, a lot of people would do this. Write this code, and then the assembler would recognize this is not permissible, but people won't understand why is this not permissible. It's not permissible because the processor does not have the pathway to do something like this. So what do we have to do is to say, okay, so we're going to have to put 5 into something first. So we're going to put it into register B because we cannot put it into register C because register C needs to be preserved. Otherwise, we'll destroy the value that we need to evaluate next. So the only place for us to put the 5 is in B, because B is going to be destroyed anyway, because of these two instructions or these two statements. So we can actually use B, at least for now, as a temporary variable. No, we are actually directly translating into assembly code now. Okay, so B gets 5, and then we can compare 5 to A by doing a CMP BA. So CMP BA is, okay, you guys can go ahead and look up the opcode table. What does it do? What does CMP BA actually do in terms of, what happens to the registers? And this is the kind of stuff that I kind of think that you guys should be able to do by now, is to go to the opcode table, look up CMP, and find out what it does. Okay, Omer is correct. Okay, so we are performing a subtraction. Okay, B minus A is the subtraction. But it's not just any subtraction, it is a binary subtraction. So with any type of binary subtraction, we are affecting the flags, right? 2 flags are kind of important here, okay, and you get to choose which one to use. There are officially 5 flags. The 5 flags are the C flag, carry flag, the Z flag, the 0 flag, the sign flag, the overflow flag, and the L flag. So right here, in order to confirm whether 5 is less than A, which flag should I use? Now you kind of have to go back to the earlier portion of the program, because A, B, and C, I already have assigned their signedness in the earlier part of the program. So I'm going to scroll back just so that you guys can see that. So A, B, and C are they signed or not? Because if that question cannot be answered looking at the code, then we have in big trouble. They are signed. Very good. Okay, so indeed they are signed. So if they are signed, then which flag do we use to indicate whether the minuend is less than the subtrahend? That is a question that relates to binary comparison. The sign flag? Nope, nope. Remember, the sign flag is not trustworthy by itself, because if the result of the subtraction is out of the range of what signed values can be represented, the sign flag would be wrong. So what should we do? The L flag, exactly. So now we have a JLI to well, since we have just confirmed that, right? So we can now say JLI to L's label. All right, and then what else do we need to do? Well, the next thing we need to check is whether 5 and A are the same or not, because by the time we get to here, we know that 5 is not less than A, but then we still have to check whether 5 and A are the same or not. So someone is going to say, oh, we just have to do this again, and then do another CMPBA. Well, do we have to? In other words, do we have to do this again just to see if 5 and A are the same or not? The answer is no. That is correct. I cannot answer the question of what LDI is going to do because that was talked about, I would say, several weeks ago. So it's important to kind of go back to those lectures and make sure that all of those instructions are understood. And also you can kind of do your own experiment, right? Just kind of write a LDI instruction and then clock by clock, edge by edge, execute that instruction and find out how the pathways are established, what register is being updated, how they're connected, and so on to understand what LDI is going to do. I can only tell you one thing. This ends up with B, register B, getting the value of 5. But how that happens really kind of needs you to do the investigation, because that's what we talked about a few weeks ago, and I suggested the activity that you guys should also be doing in order to understand how the instruction gets the job done. So getting back to this context here, we can just follow up with a JZI because the Z flag is also set when we execute the CMP-BA instruction. And for those of you who are thinking, but how is the Z flag also set at the same time? Well, to answer that question, you have to look into the ALU in the processor, okay? Because when you look into the ALU in the processor, you will find out how the Z flag is affected by the result of basically anything that goes through the ALU, with the exception of increment and decrement. Those are the only two instructions that do not affect the flags. So the Z flag is also affected by the compare. If B and A are indeed the same, then the difference is going to be a 0, which means the Z flag is going to be set. It's going to have a value of 1. So these 4 lines are basically implementing, this is specified in TTP ASM, and those 4 lines in return is implementing this line of C code. So now we have our first translation from C code into assembly code. Are we good so far? All right, cool. All right, next we have something that looks like this, but it looks like it's going to be easier, right? So I'm going to comment out the C code that I am about to translate, and then we'll go ahead and do the translation. All right, so this one is actually easier because I don't have a constant, okay? I'm just comparing A and C, and they're already in registers, and they're already in the right order as well, okay? Because you want the whatever you want the less than operation to be specified in this order in order to just use a CMP. So we have CMP AC in this case. We are comparing register A to register C, which translates to subtracting C from A, but without storing the difference to any of the registers. JLI again, because it is a signed integer, so we have to use JLI in this case, also to else label, and then JZI to else label, because we have the equal to also check for. So JZI would be, the Z flag would be 1 if and only if A and C are the same. So that's why we can also use JZI for that. And so these 3 lines in assembly code is implementing this line in C code. Cool. And then we have this line in C code again. We have to translate that into assembly code. So with this one, I'm going to do a CPR BA. In other words, I'm copying A to B. So this is basically saying B equals to A. And then we can just go ahead and add C to B. So that's just that. Okay, B plus equal to C. And then we have the next line, which is a goto. Gotos are super duper easy to translate. Why? We want to continue execution at the label of end if label. This is how we, the goto is how we specify that in C++. How do we do this in assembly code? How do we specify where do we want to continue execution? That's close, Mark. You are almost there. JMPI is correct because JMP depends on the register. You have to first provide the address. You have to first put the address where you want to branch to into a register. Then you can use JMP and then followed by a register. JMPI, the I is the immediate portion, which means you can use a label for that. So there we go. Cool. All right. So label definition do not need to change because the syntax of a label definition is identical between C++ and TTP-ASM. So these we can just leave it alone. So now we just have to translate this line of code, which is first to comment out the C code. But this is almost the same as the other one, CPRBA, or BC this time, because we have to subtract A from C. So we copy, basically we have B equals to C, and then we have the subtraction operator, instruction. We are now subtracting A from B, like so. And then the end if label can stay here. I think we are good to go. What do you guys think? Let me take a look at the time. We got 7 minutes before the end of today's lecture. I think we are good to go. Ready to test it, right? All right. So let's go ahead and test it. And let's see. Let me get to my assembler. Now I could use a river spider and just bypass the whole thing, but I don't want to because I want to look at how labels are defined. So I am going to the assembler, and you guys can follow along if you want to. That's one kind of cool thing about the assembler being a spreadsheet or Google Sheet is you guys can all head out there and basically flip around, look at all the different sheets, find out just examine different things if you want to, take a snapshot of that, right? Make a copy right away so that you can examine it later on. So all of those things you can do, which I think is kind of cool. Alright, so we have a leftover program from before. I'm just going to remove that program first and then go back to my notepad and copy the entire thing from here to here and then paste it to A1, and I'm going to put a no op or halt all the way down here, just so that the program would stop at the end. Alright, so the assembling is okay, and we can now go to RAM file. The program is not really that long. Okay, but before we do this, okay, I remember Bilal's question, which is basically what is a label? Okay, so when we go to the Assemble tab, it will be very clear what a label is, because when you look at the definition of a label, which is line 19 and also line 15, these are label definitions, right? So the else label as a symbolic name is really the same thing as what we know as 16, okay, in base 10. And then the label and if label is really the same thing as what we know as 18 in base 10 or 12 in hexadecimal for end if label, and 10 in hexadecimal for else label. Now if that is not enough to convince people, okay, these are the values of the labels, you can always go to a kind of funky tab here called Sim tab, which is the symbol table. Okay, for those of you who will be taking compiler classes, this is symbol table. So when you head out to this tab here, it will basically show you the internal stuff that the assembler needs to track. Let me magnify this a little bit so that you guys can see a little bit better. So when you see else label, and you can see how else label is defined on line 14, and then RPN, which stands for reverse Polish notation, which is the postfix notation, it has a value of 16. This is 1/6 as in base 10 16. And then with the other label, which is end if label, it is defined on line 18. And coincidentally, the value of the label is also 18. Now, the address part, you don't have to worry about it. You just have to look at the RPN, which is the value of the label. So I hope this kind of gives you guys an idea of what resources is available to you to understand what a label is, how it is defined, and so on. All right, I'm switching back to a smaller font now, and go ahead and download the code. All right, cool. So we'll go to here, download, and we want a CSV. There we go. And we'll call this, I'm just going to call this test.csv because that's all it does. Okay, it's just testing stuff. All right, so now we need to start up Logisim. I'm just looking at the time. We got 2 minutes left. I think we have enough time to at least go through one iteration. All right, so we'll go ahead and start at Logisim, and then we have to go to Documents, CISP310, River Spider, Processor. There we go. All right, so now we load the program into RAM. Okay, so go here, right click, load image, and then we specify /temp. Not sure whether you can find it that way. Let me redo this so that we can point it directly to the temp folder. There we go. And then the program is called test.csv. Right there. There we go. So you can see how the program is now loaded. Now this program is not going to be easy to test, okay? Because how do you know whether the program is doing what it is supposed to be doing? So what you need to do is to go back to the C code, because the C code is a lot easier to understand. And then you ask, okay, how do we test whether this program is working or not? So one thing you can do is to say, okay, let's make this condition true, okay? And then in that case, your B should be the sum of A and C. And if you want this to be tricky, you also want to test whether A is interpreted as a signed value. So you want A to be -1, and then you want C to be even more negative than that. Let's say -2. So let's test that, okay? So we want to test it with, okay, so I'm going to comment here and say, test case A is -1, C is -2, because we want this condition to be true. We want the conjunction to be true. So A has to be less than 5, and then C has to be less than A. So -2 is less than -1, -1 is less than 5. Now, if I made a poo-poo in this program, instead of using JLI and I used the JCI, then the program would behave incorrectly, because -1 is sharing the same bit pattern as 255 in the unsigned interpretation. So these are good values to test, okay, if I want to confirm whether the program is going to do this or not. So if it is going to do this, B should end up with -3 as a value. All right, so what do we do now? We switch back to the processor. We go into the register bank and manually plant those values in. So -1 is the same as FF in hexadecimal, and then -2 is FE in hexadecimal. Now, if you're asking in your head, how do I figure out, the hexadecimal representation of a negative value represented as a signed integer, I am going to let you guys think about that question a little bit, okay? Because we have already addressed that question in long ago, so you probably want to kind of go back to the notes or the lecture to find out how to figure out the bit pattern of a negative value in signed representation. Now we switch back to main and we're ready to run the program. So when you're running the program, you kind of want to keep an eye on the halt flag, because when the halt flag or the halt pin becomes a 1, that means we have reached the halt instruction. Typically, you don't have to worry too much about it, but just in case you did not put in the halt instruction, the program will keep going and going and going, and so it's good to keep an eye on it. All right, so tick frequency is 32 hertz, which is kind of slow, but it's going to get the job done, so we'll go ahead and just let it do it. Okay, so now the halt is 1, which means I can now stop simulation, disable ticks, and go back to the register bank. Now, before I go back to the register bank, I have to think about what is supposed to be in register B, right? Because register B is the sum of register A and register C according to what the C program is supposed to do. So that will make it -3. And now we have to think about what is the representation of -3. So if FF is -1, FE is -2, even if you don't understand anything about hexadecimal, binary numbers, and whatnot, what do you think is the representation of -3? Exactly. Those are the kind of things that they ask in IQ tests, which is basically trying to figure out patterns, right? So now we can go to register B, and we can click on this wire. It's going to be the same thing. And we can see it is FD indeed. So in this specific test case, the program worked. Okay. So obviously, if you look at the C code, this by itself is by no means any verification that the code is working 100%. But it does give you an idea of, okay, so this is how we test it. So the next thing you want to test is to see if the program would go to this branch here when A is exactly 5. Okay. So if A is exactly 5 and A is still greater than C, are we going to end up in the else branch, and so on? So if this is if you want to get into this kind of stuff, really understand how this program works and so on, I would do something like this. I know we are running out of time, but I would still kind of want to give you guys some idea of what you can do at this point, because this is one thing you can do, is to put a no op here. Now, the no op doesn't do a single thing other than taking up just one extra byte, and it's going to be 0, 0. But this allows you to run the program in the CLI, which means you can now get the trace. Once you get the trace, you can put the trace into the analyzer, and then you can actually get to see what is happening when you perform the compare, what flag is set, what flag is cleared, which conditional branch did we take. Okay, did we take the JLI? Did we take the JZI? Did we take the other JLI, the other JZI, and so on? So that gives you the ability to really kind of test the program. Now, if you do something like this, if you want to run this program from the command line, you probably want to preload values into register A and register C. So with our current thing, you want to initialize register A with -1 and initialize register C with -2. But you can change how you do the initialization to basically look at different test cases, and then you can look at how the program performs the branches, how it performs the comparison, and so on. So once again, these are suggested activities that I think is going to be helpful. But now that we are done with this topic, we are getting back to the lab for today. I'm kind of surprised that nobody asked me whether there's a lab today or not, but there is. The bottom line is there is, because I just made it this afternoon. I just made this specific lab just so that you guys get something to practice. And the lab is called Compiling C Control Structures. There is a passcode to it. Oh, I'm not taking attendance anymore. There's no point in taking attendance anymore because the last day to drop is already gone. So, people can miss classes from here all the way to the final exam, and there's not a single thing I can do about that. But the point is, I just want to make sure that people attend the class because I think that is important for people to succeed in this class. So if people don't want to be present in the class, and that's why I chose present as the access key of the access. Oh, that's not what I want. So present is the access code of today's lab. And let me go ahead and save and publish. There we go. All right, so just one more thing before I let you guys loose to kind of do what you need to do is this lab has only 6 questions. They are all multiple choice questions. So I know from the pattern that I see, when people attempt these labs, some people just kind of do the infinite monkey approach, which is, I mean, it works. I mean, people can get 100% score in these labs by using the infinite monkey approach, but that's not going to help in terms of understanding the concepts. This lab was specifically designed to help you understand the material that we have just talked about. There are only 6 questions. You have 80 minutes technically to do it. Unofficially, you have until 9:50 p.m. tonight, which is like almost 3 hours to do it. So I would spend the time, and have the patience to kind of look up, the material from previous weeks, such as binary comparison, what the flags are representing, going into the processor, find out how the Z flag is organized, and so on and so forth in order to answer those questions, because that is basically how you study for this class. Is to look into those things. I mean, everything is already open sourced. Even the assembler is open sourced because it is in the Google Sheet, and the Google Sheet is not protected in any way. So when everything is open sourced, how do you study? I mean, it's not about memorization. It is about understanding the material. So you got to spend some time to really kind of think about the question and think about how am I going to answer that question. Yes, I'm nagging here, and I'm done nagging. All right, so you guys go ahead and do what you need to do. I'll be back in about 10 minutes. That's it. So I'm going to get out of the voice channel and stop streaming now.